The thing that should help you in the homework, the reason I decided to do the domain wall, that you guys should do the domain wall, is remember when I talked about the tunneling, and I said we get a bubble which has a wall. After all, what is this bubble with a wall? This is actually the domain wall. You know, if the radius of the bubble is very big, then it's really an infinitely flat surface, just like the Earth is for you and me, right? I mean, who cares that Earth is spherical? That's why they thought for a while that it wasn't, actually for quite a while. So, and then I argued, remember, it will cost you energy and so on and so forth to cross the wall. And so the fun of it, you would actually see it explicitly. I gave a physical argument there, right? I prepared you. And then the idea is that you actually solve for this static solution. All you have to do is forget that there is time, right? We want a static solution with a finite energy, which I explained. So you compute, you look at the energy per area to be finite. Energy will be infinite.
But in the homework you said that suppose that phi only depends on z.
Right, this is this direction. It will be for a spherical bubble, that will be r.
So yeah, we can take it to
right, but I took, no, but what the homework is not a bubble, the homework is infinitely large, which applies very well when the wall is very thin. So what the Coleman does is the explicit calculation for a very, very thin wall. That's equivalent basically to a large approximation. At least the solution looks basically the same. Right? By the way, who wants to go on? The physics of domain wall is fantastic. I can't help making this remark. This is really nice. You know, when you do your studying gravity, but some of you may know, you will learn that when you go to the sort of Newtonian limit, and you ask what happens to someone like you and me near whatever object. It's strictly speaking not Newtonian limit what Einstein does. Remember, in Einstein case, remember, you know, I don't know if I should say remember or you know it. Two things actually, it's the density and the pressure. And the pressure, of course, is zero. When you have an object like this, the pressure is zero. It has to do with the energy momentum tensor. The Einstein equation, you might have seen that, right? If you know energy momentum tensors, you can do everything. It just, Newton gives you a density. Einstein gives you energy momentum tensor. And it has to be because he wants to apply to a relativistic system. Now, domain wall is a relativistic system, of course. In general, it's a relativistic field, which is called. You see, the field is trapped in this tiny region. If you read my little note, the first page of the homework, where you are at the maximum. So when you go to this limit, which would be Newtonian, it's a funny thing. The energy momentum tensor of the wall is very funny. So the static domain wall is actually anti-gravitational. It would repel you. This is beautiful. The density is positive. It will still repel you. Now that's kind of amusing. It's a really fascinating object. It's what we call topological objects. And we just finished to make it sort of clear physically. Then I said, really what is happening in this so-called solution, you're going to find phi classical of Z, which you sometimes I call phi domain wall of Z, with non-trivial boundary conditions. Remember I said when I look at the system, there is a trivial solution, for example this. And the boundary conditions in this case has, as Z goes to infinity, plus infinity, or minus infinity, phi goes to phi 0. This is the boundary condition. And then phi is phi 0 minimizes the. This particular solution is actually static. You minimize both the kinetic energy and the potential energy. But if I want a solution so that when Z goes to plus or minus infinity, I'm asking that phi goes, let me call it classical, to plus or minus phi 0 or V. then of course it cannot be a constant, right? You understood the picture that I drew. If this is phi classical and this is E, it looks like this. It has to jump, right? So the way it goes, and it has to pass to 0, it's symmetric in Z going to minus Z. So there is a region when it's caught here. So what I did is a step function, and you of course you will get some exponential function, which is a good approximation. Okay. And that will help you understand why I argued if it is true that there is this energy hidden here, then you will have some kind of tension, you could call it whatever energy that you require to cross the wall times the area. Remember I asked you when you have the energy of the bubble, it's minus delta V, because it's, here is the true minimum. And this goes as R cubed. And then there is something that you're going to compute. On dimensional grounds, you could guess it. And of course, times R squared. It's very thin. The only thing that matters is the area. Okay. So these are topological solutions, we call them, but they have to do with these mappings. You see what I'm mapping? I'm mapping the manifold of infinity. You can always define manifold of infinity depending on the symmetry of your solution. In this case, manifold consists of 2 points, very far from my desk. This is my domain wall, my desk. Okay, it's very big. Well, it's not so thin, right? You have to need some imagination, a little thinner. So the manifold in infinity, we can define it. It's all the points, in this case there are 2 points, right? Z is plus or minus infinity. The manifold, the vacuum manifold, is plus or minus V, 2 points. So I can have a well-defined map. It can be trivial. When I map 2 points, it's always one and the same point, or maybe non-trivial. So vacuum is a kind of trivial map, if you wish. I'm mapping a non-trivial manifold of 2 points onto 1 point. So, you see, if I have a vacuum manifold later, which is a circle, which is a comment en passant, I want to know whether there is a similar solution. I need a map. So I'm going to take an infinity, which is a circle, which means I'm going to look with a solution with an azimuthal symmetry, right? This is what I told you that I expect I could get a string, even being a dummy, you know, without knowing anything. I could have, because I have a well-defined manifold, vacuum manifold circle, so if I take an infinity to be a circle, I can have a well-defined map. So I could map the circle at infinity to 1 point. That's a constant. That's vacuum. It costs me no energy. Everything is 0. If I do a non-trivial map, it costs me energy, and I get trapped. And that's well, anyway, I may come back to it. I may not. All right. Any questions here, please, on this? Since I want to leave the domain wall, I have to go on with Nambu-Goldstone. Okay. So let's try to recapitulate what we've learned in the sort of Nambu-Goldstone picture. Nambu-Goldstone, spontaneous symmetry break. Up to now we did the U1 example. We took a scalar field. By the way, why did I take a scalar field? Why did I have to introduce a scalar field? Look, I'm doing this what I hate to do. Remember, I told you I'm a minimalist. I never change anything unless I have to. And by the way, this is as I was driving here, I was thinking, When I teach you the standard model here, I teach you the standard model because the standard model is there, but I'm trying to do something else. I'm trying to remind you or tell you what it means to have a theory of natural phenomena. I've been using this term, I liked it. Weinberg used to do it, of natural philosophy. There is nothing philosophical about natural philosophy. This is how Newton defined very precisely, very serious phenomenological physics, which natural philosophy means you can philosophize all that you want, but I want you to be natural. That is to describe the phenomena. That is to say, to have a theory which is predictive. This is why the same Newton, you know, who was not completely stupid, actually says, I know there will be messengers. I'm not a fool. I don't believe that the gravity can act at a distance. But I have no means of describing that. And me being a natural philosopher describing the phenomena that I can describe, I will assume that the force acts at a distance. Why he does that? Because then he does the following. He gets the law. He writes a universal law which has to do with the, you know, inversely proportional to distance. He had epiphany, right? He was throwing little stones on the hill. You know that, how it all happened. And he noticed that when you throw the stone, okay, I'm sorry to bug you with that, they fall down. But if he hits it stronger, it falls down further away. And all he had to do is to imagine a giant. He was strong enough to throw a stone. And he realized it would hit him back in the head. And then it all got clear. But what is crucial then afterwards? What I want you to remind you here, what Feynman says very neatly, if I suggest you strongly to occasionally watch the videos of Feynman, says it's very simple. You make a guess. I don't care who you are, I don't care how smart you are. There is nothing profound about that. The greater you are, the deeper and the more meaningful the guess will be. But then you compute. If you can't compute, shut up and try another guess. So eventually you make a good guess and you compute and you get an answer. And then compare with the experiment. There is nothing else. That's physics, he says. Occasionally he actually gives you an advice to you young people, and to me he gave when I studied out. He says you will hear people talk about things it will look like physics, it may smell like physics, it may taste like physics, but it's not physics. Physics has to satisfy what I'm saying, he says. Feynman was not completely stupid. So what is good about Newton and Einstein, for example? Then Einstein writes this, we write the Lagrangian or equations, and then he leaves it. There are no more conjectures, no changes, no discussion. It's not that he comes every 5 years or every year or every 5 months with some change of that thing. He tells you, oh, I'm sorry. First he says, oh, I have a beautiful idea. But he doesn't agree with Newton at small velocity. Would you listen to him? I wouldn't. Because I studied with Newton. And Einstein would have written that. This is, for example, what the loop gravity does. They don't have a Newtonian limit. And yet many of you tell me that you want to work on something fundamental which doesn't have a Newtonian limit. Or, imagine that Einstein says it, well, I don't know what a vacuum is. Like I have to find it. And then he realized that he has infinitely many vacuum. Oh, geez, he scratches his hand, what to do? But he says, maybe I'm lucky, maybe I will guess it. I have a divine inspiration. Just hang on. Of course, the times are passing by. Goes on and on. Then he realizes it cannot be done. Then he says, oh, but let's forget it. Let me just imagine that there is a landscape of vacuum. What a funny word to use. Landscape, this is the beauty of the Alp mountains. If you had more time and money, you would go and ski now on the weekend, okay? Magnificently beautiful, okay? And so on and so forth. And then will come the words will be called swampland and so on. And I told you I wrote this article recently. The reason I wrote it because of you guys. Because I've been worried. And I'll try to stop here and never bug you again. I'll try. It's not easy. Then I'm worried that you heard these buzzwords and you don't understand. If I ever come here and write something and claim it's a model, And then I keep changing the debating it, you know, and the time goes on. Don't listen to me. What you want from me is not that I derive the things. You want from Einstein that he gives you that, and he goes away. And then you do it. And this is a nice example of a simple and profound physics, and it's always like that. Great physics is simple and profound, and it asks one question, not two or three, never. Okay, none of this great works in the past, where I encompassing all of physics. Typically, they were asking really simple questions, you know, the falling of stones, the motion of an electron, or a neutrino. So here the question that I ask, what will happen? What will happen? Can I imagine a situation in which I have a continuous symmetry and everything is symmetric, but my ground state breaks it? So that continuous symmetry I could imagine could be charge. Well, I don't like to do that. Charge seems to be a good symmetry. Or maybe that's some charge associated with the SU2 weak interactions and so on and so forth. But why am I taking a scalar here? Why am I ending the scalar? It's very important with what we do when we do physics, you and I, to stay minimal. No prediction can be made if you move from minimality. Okay, this is crucial. So obviously I don't want to introduce the scalar. Don't tell me, of course I know there is a Higgs boson, okay? It took a long time for people to be convinced that they should look for that, okay? Because people objected from the beginning. Why in the world do I need an elementary scalar when there are no elementary scalars? So make long story short, why do I have a scalar here? Why I'm not taking the same gauge boson that I will have in my theory eventually? See, what I want to achieve, remember, all I need to achieve is that when I write down the vacuum manifold, which is the points of all phi 0 that give me the minimum of the potential, or minimum of the energy, really, I should say, because I'm looking for a constant value of the field that minimizes kinetic energy also, obviously. Remember what I said. I want to get these points so that they are different from 0. Why? Because strictly speaking, what I have here, let's be more precise, is always the generator of my symmetry, you agree? Right? A continuous symmetry generated little by little by. And I'm saying that Q phi is 1. So phi 0 to 0, phi 0 being non-zero is equivalent that Q phi 0 is not equal to 0 by definition. Because why? Because Q phi 0 will be phi 0 if it is not 0. Every phi has to satisfy this, right? Or Q phi is phi, I'm sorry, not 1. Q is 1. Look at the Q phi is equal to 1 everywhere. I'm sorry. So this is also equivalent. This is also equivalent to, when I say this is equivalent of U acting. I should never forget to introduce U e to the I alpha q, my U1 unitary transformation. So U acting on phi 0 is different from phi 0. I have a non-trivial vacuum. That's what will imply spontaneous symmetry breaking. If the vacuum is trivial, then when I act on it, it will not be moved. It will have nothing. That's what was supposed to be. That's why we called it vacuum before. We keep the same name, but it's not a good name, obviously. It's a ground state, but not a vacuum. It carries charge. So why do I need a scalar? The reason that I need a scalar, actually, I want to arrive to the physical theory of the standard model in which V will be the scale of weak interactions, which will be around 100 GeV, which is the scale that we do experiments today. We are actually above it, fortunately. at the LHC. And I have to make sure that at the energies that I do experiments, I don't break sacred symmetries. There are symmetries that we don't see breaking, okay? We proclaim them sacred for the time being. Tomorrow they may be broken. Charge, color, and Lorentz symmetry. Rotational symmetry. Boost symmetry seems to be a good symmetry. Therefore, I cannot take a spinor or a vector boson. I would break Lorentz symmetry immediately. If I take an electron, I may break the charge. This is the necessity of introducing the scalar. So this is when the minimality becomes non-minimal, if you wish. You couldn't have what you had before. Okay, that we can live with. Okay, that's very important. And then it was not so hard, right? We wrote the Lagrangian, which was 1/2 d mu phi star. Phi must be complex, minus lambda over 4. Or I actually wrote it as lambda phi squared minus v squared over 2, I normalized. Simply because I like to write phi, as most books do. Actually, I typically don't. In my notes, I think I don't have this, but it doesn't matter. Square root of 2. You can put it, sorry, here. You can put it here, you can put it here, as you like. And we found out that, of course, in this case, the vacuum is non-trivial, right? We've chosen phi 0 to be v over square root of 2, a particular vacuum. And then we wrote phi as v over square root of 2. How did I write it? 1 over square root of 2, I'm sorry. V plus h plus ig. And I sort of call this a renormalizable variable. Just the language. And I found out that mh squared, you remember this in your dreams soon, and you could have guessed it. It has to be proportional to the scale, and it has to do with the coupling. You see, this scalar that we ended up calling Higgs in the gauge case, Higgs or Nambu Higgs or whatever, it gets its mass like everybody else by coupling to its own vacuum. You see, it lives near the vacuum. It knows about it. Therefore, it has to have a mass proportional to the scale. And it has to be proportional to the coupling. If lambda is 0, it won't know that there is a non-trivial vacuum. So, for example, a gauge boson, you can make a guess. What's going to be a mass of a gauge boson? It's going to be proportional to V, where what will enter will be a gauge coupling. What else? And then we found that mg is 0. And then we added a fermion. This is just to remind you that the left and right, of course, fermionic fields, they never know about each other, right? They are the fundamental quantities. A left-handed field, if you leave it alone, if you don't do anything to it, will always move and stay left-handed. You know what it is when the particle is massless, then the only thing to talk about is scalicity, and that's preserved. You can't change it. And then we said there will be a Yukawa coupling, a Yukawa Lagrangian, I call it, which was Yukawa coupling times, how did I write it? Psi L bar, psi r, phi, plus Hermitian conjugate. And what did I find out? Remember that the Yukawa, I think I got Yukawa over square root of 2 is m psi over v. I found out when the dust settles that from here I will get the coupling of the Higgs I already started calling it Higgs, is proportional to m psi over V. You see? Psi bar psi. Agree? Yeah? I'm boring you, or I can't judge, you know, it's trivial, you already have it, okay, or it's 11 o'clock in the morning, you know, I'm very sleepy, I got up very late, that's why I was a little late. But it's easy to wake yourself up when you teach, right? It's another thing when you have to listen to someone. And then we had, I think it was with a minus sign. Well, I'm not sure, because I always forget whether I put the sign. The sign is not important here, not yet. The relative sign was minus, that I remember. And we had the same m psi over V, G. There was a tiny difference that this guy was coupling to a pseudoscalar. One is a scalar, the other guy is a pseudoscalar. And it made all the difference. You see, this guy is like a graviton, at least in a static limit. It couples to your mass. So for example, if this guy was massless, it would be extremely dangerous because it would mediate the fifth force and it would destroy gravity. Gravity would die immediately, right? This is why you know that this guy has to be very massive. Unfortunately, it is very massive. The mass of this guy, as you know today, is actually a little bigger than the W boson mass. Maybe you know the number?
126.
Right, 100, whatever. 25, I remember. 26 maybe, you're right. GV, so that's of course dies off immediately. That a GV corresponds to, you know what distance? Roughly, what is the size of the proton? It's very small.
150.
Yeah, what is it in, I'm sorry, I forget. This is very funny. I know everything in centimeter. I know the size of the universe in centimeters, you know, cosmologists laugh at me. And I know the size of the proton.
I think it's 10 to the negative 14 centimeters.
Roughly, okay. So for GV to the minus 1 is roughly, you are saying, let's write like this, 10 to the minus 14 centimeters.
I think there's a factor of 2.
Yeah, maybe even 3. A safe factor is always to put 3 because it's pi. You know, we always say pi should enter there. Like if people ask you how long is a year, how many seconds? It's some number around 10 to the 7. Put a pi there, it works. Well, you have to remember the order of magnitude, you know, that's
10 to the 7 seconds.
So sometimes we have these funny derivations. Anyway, so you understand something is 100 GeV heavy, talks about 10 to the minus 16 centimeter, it dies off immediately, right? It dies, weak interaction dies, it's on a scale smaller than the size of the nucleus, right? It's a very tiny scale. So we don't have to worry about that. We could have worried about this, but we decided not to, and that's your homework. I want you to quantify it a little bit, because this will be proportional to the spin, right? I cannot over stress it. We can have massless number boson bosons. They can be completely massless. We can get really a long range force that spreads all the way from here to the sun. But there is no danger, because luckily enough spin, being a vectorial quantity, has to sum up to a small number. And I tell you in the homework, it can small up to 10 or 100 or 1,000 or 10,000 or million, who cares? There are really a lot of protons. I want you to dig up the number, okay? Try to dig up a precise number. After all you have to read is the mass of the... So we have a long range, harmless force. That's kind of interesting. It's something new, if this such device would exist. Now notice a very important thing here that will be it will be essential when we come to the gauge case, but it's already present here. You see, I tell you that I have a theory of mass. I tell you, look, I found out I'm a creator of this, of course it's not me, and I tell you, look, I know where the mass gets its origin. It comes from this vacuum which is charged. So why would you believe me? I mean, why in the world, how would I check that I actually live in this strange vacuum? I have this terrible thing like a fish in the water. how can the fish know that it lives in the water? Or a human being breathing air, you know it when there is no air, that you actually live in this ether of air. So there are two ways the fish can know. Well, fish knows, of course, when it's fished, as epiphany, and then unfortunately cannot tell anybody that it lived in this vacuum. So what should you and I do to check? It's a good moment to pause and say immediately, because this is the most striking aspect of what the standard model became. This is sort of the beauty of how the great discoveries happen. They are not anticipated by great Baroque ideas, never. Dirac is shocked when he finds out that there is a positron. 1928, Dirac writes this little equation that you know, this little Lagrangian that I keep writing there. He notices there is spin. Then he notices there is a positron. He doesn't know what the hell to do. This is 1928. For 3 years, he'll do all kinds of song and dance. Look how serious the times were. He was scared. Terribly scared. If he says that there is a positron, if there is no positron, his reputation will suffer. Not today. You can keep saying that, you know I have a theory of everything, you just keep saying it. The reputation depends on what other people say about you. This is a very crazy time in which you live. I want to emphasize to you, I'll tell you something very important in a minute, why you should be careful. But Dirac even says that positron is a proton. You know this? He said, because he's scared. But you know they should have the same mass. In Dirac's equation, it's the same mass particle. He says, well, there is a little problem. Proton is a little heavier, 2,000 times heavier. But maybe we understand it. Then Oppenheimer wrote a paper saying this is nonsense, right? How would hydrogen be stable? And then in 1931, he said, yes, there is a positron. This is interesting. This is sort of being too conservative. This is another danger that we should watch out. And this is why it's very important. In 1929, there was a graduate student at Caltech called Chow. He was doing cosmic ray experiments. And he was getting particles. You know, you check what the particle is because you have an electric field. He was getting particles that were moving in the opposite direction from the electron. So he was running around the corridors of Caltech, telling everybody that he's something crazy. He discovered a positron. I mean, you're young, you can think about what the message is. He obviously made a mistake, or two mistakes. He told everybody about that, but he didn't publish a paper. They hashed him up, they said, you're a moron, repeat this, there are no particles. Electron is an electron, how can it move? This was in 1929, 1930. In 1931, Dirac said loudly, you know, he's got courage, there is a positron. There was a postdoc at Caltech called Anderson. He immediately repeated the Chow experiment. He got a Nobel Prize. Well, that's been contested, you know, people, whether it was a really good behavior or not, it's another story. So you see, whether or not the discoveries are made, sometimes depends on the atmosphere, because you have to recognize when a new revolutionary idea, theory appears. And it has to do in which kind of mood you live. Okay, this is an example, I'll give you a few as we go along. So I need to be sure, I have to convince you that I live in the vacuum. Let's think about it. How would you and I test this idea? And this is remarkable, you see. Why am I doing this? I want to have a theory of weak interactions eventually. You see, this is what so I need to have a theory in which W is massive. But I can't break the symmetry. I cannot give it a mass, because if I give it a mass, it doesn't work. We did this program, so we have to do this. So it's really interesting that starting with the modest goal to understand just weak interactions with the exchange of a messenger and have a consistent theory which you can compute led to the theory of mass. It became something far more important. Now we know, well, you will learn details. now we believe it's still to be tested to the bitter end, that the elementary particles get the mass from the Higgs mechanism. How do we know that? How do you think? Where is it? Here. Okay, I'm sorry for this dialogue, but I want you to sort of think along the lines, not just be hit with the facts. You see, what is the theory? You will often hear as you go to seminars, or you may read reviews, people often quote, even say that there is a problem of mass in the standard model. That people say, you know, there is an electron mass and a muon mass and the up quark mass and the down quark mass, and I cannot predict them. They say, they call this a problem. This is very strange. The theories never predict the parameters. What the theories do, use this number of parameters to correlate physical processes. And I find it very strange because this is a wonderful theory of mass, dynamical theory. And why is it a theory of mass? You see, because mass is not a static parameter anymore. Yukawa is an interaction. This is new. You give me a mass, I will know the interaction. I can test the idea. I don't have to actually get out of this vacuum, get out of the water. By the way, one way you can imagine that you will get out of it, if you heat it up. When you heat up your physical system, you go through phase transitions. That is not surprising that you do that. And it can be proven rigorously that if you heat up the standard model, this model, like, it doesn't matter. What does it mean that you heat it up? You have to go to the temperature that is much bigger than the scale of the theory. You can prove, we know that the symmetry gets restored. At very high temperatures. Very high is defined as much bigger than the scale of weak interaction. This is in my physical system would be the scale for us will be the mass, the mass of the gauge boson. That will come later, it doesn't matter. So this is on the order of 100 GeV. So if you go to the temperatures much bigger than the 100 GeV, you would actually see the thing. You would be like fish coming out. You would be like dolphin. The trouble is that this temperature is very, very low. I don't know if you have an idea about the scale of the temperature. You know the temperature in these units? For example, the background radiation. That's very small temperature, right? That's very nice. It's about Kelvin. You know how big is Kelvin in GeV? Or in other words, how many Kelvin is GeV? Or electron volts, let's say, how many Kelvin, roughly? I think there is a pi here also. I'm never sure. It's 10 to the 3, 10 to the 4. I think it's pi times 10 to the 3, roughly. Or maybe 10 to the 4, roughly. It's about 10 to the 4 Kelvin. So already electron is hot. Sorry, electron, EV. So GeV, so 100 GeV is what? 10 to the 15 Kelvin. That's terribly hot. At all there's an orders of magnitude about the, you know, the temperature in the sun's core. Okay, this is a science fiction temperature.
At higher temperatures, the mass doesn't disappear.
Yes, the vacuum expectation value will go to 0.
So at high temperatures, we don't have mass.
Well, it's a delicate thing. Strictly speaking, right, at high temperature, the particle doesn't have a mass. The only thing is, you remember, inside in a very heavy object, the temperature itself has a scale. So the particle behaves as some kind of plasmon, we say. A photon inside the sun behaves as if it has, there is a difference. It's not massless, it's just different. Yes, it's massless in the fundamental field theory level, but the temperature can mimic, okay? So you would have to think hard how to really disentangle that, but you could. The answer to you, yes, strictly speaking, V will go to 0. In this theory, when we go to 0, the mass will go to 0. These were ideas by Kirchnitz, and then Linder followed. I think he was a student of Kirchnitz in the early 70s, and there is a beautiful paper by Weinberg, particularly beautiful in my opinion, that has a typical Weinberg has a paper that discusses in a general arbitrary theory with arbitrary gauge, Yukawa, scalar couplings, establishes this fact. In the standard model that has been a careful study of many years. So we can know that. So the only thing that we have that we can do is do the following. I can immediately compute the decay of the Higgs into the fermion. Right? And that will be one of your homeworks, but you can immediately set gamma h going to psi bar. It will be proportional to Yukawa square. Okay, tell me without doing it. You had a question maybe?
Yeah,
yes.
I have a question. So an interesting part of the theory is that now masses are a dynamical variable.
The masses are dynamical variable. This is beautiful. So instead of speaking of the problem of mass, you should actually say we have a fantastic theory of mass. And I will make you appreciate that by telling you how, you know, there is a miracle how it works in the standard model. Sorry.
I'm worried that originally I have n mass parameters for n particles. Now I have n couplings for n particles to describe their masses plus an additional new field.
Well, I have for every particle I have a coupling, right? So I have to know the mass. All you have to do, you know, Weinberg writes this paper, let's say, okay? You have to tell Weinberg, okay, so that he can do the calculation. Well, you can do the calculation, forget it. Someone gives you the mass, you can compute the coupling.
But I increased the number of new parameters in the theory.
No.
I have now the same number of
as
parameters
before
for couplings, plus
yeah.
a new field and new vacuum expectation value for the Higgs field.
Well, there is just one vacuum expectation value for all the particles.
Yeah, but now
that I include. That's the mass of the W boson.
Now I have n plus 1 parameters. When originally I only had n.
Well, I will discuss this at length, but I'm glad that you asked, so we anticipate that. We'll come back to this important question. I will find out that MW, as you can guess, is G times V, gauge coupling times V. What else would be there? We'll see that explicitly. So I have a parameter V, which I don't know, so you're saying I have a parameter W, but it turns out that W mass will be related to the Fermi coupling constant because I will reproduce weak interactions, okay? Now, some people say, and I find it very strange, and I even think Weinberg himself would occasionally say that, and I find it very strange. There were times when I believed that, I succumbed to that. I have also, when I was at your age, well, bigger, maybe not immediately, but a little after my PhD, started to worry about why there are so many parameters, so can I have a better theory of mass? So you understand, I need to imagine some kind of symmetry between these fermions, which is somehow broken, and then reproduce the spectrum. But think about this. What we like about the normalizable field theories, this fancy language that you use, is that you can compute any process in the world. There are infinitely many processes you can imagine. You want to scatter a W boson on the photon, you can compute that. Scatter a photon on the electron, you can compute it. Scatter an up quark on the down quark, whatever you do. Now, I can compute infinitely many quantities, and you are worried whether the number of parameters is 3 or 7 or 10. Who cares? Would it be really much better if you can calculate infinity with a few parameters less? It seems that you're not appreciating the great success, and I think this is not appreciated of field theory, which is culminating with the standard model, is this miracle that a finite number of parameters allows you to compute infinitely many physical quantities. So I would not worry anymore. I used to, by the way, and I would work on this, and nothing came out of that now. By the way, one way of knowing you guys should be wary. I apologize to you. When I teach you here, when I speak to you, I make the following assumptions. That you are intelligent. I apologize if you don't think so. And that I'm intelligent. I apologize if it doesn't appear to you, okay? But I have to do it for the sake of our communication. I also imagine that you really want to learn and understand what is going on and not be confused. And then you want to take seriously what we do there. This will be crucial. So one thing of knowing that you are probably on the wrong track, if after 40 years you don't come up with a single prediction, single improvement, think about changing the road. Okay, normally good theory, you get predictions in 2 days. Okay? Remember Einstein theory, the reason people went crazy about it, you could immediately compute it. And then computed mercury perihelion. And 6 months later, it was tested. So this was the, so I mentioned in 84, I took a sabbatical. I used to work at Brookhaven, and I went to Santa Barbara. There was like a long workshop, 6 months, organized by Frank Wilczek, was at that time at Santa Barbara, Lee Wolfenstein. At that time, there were people like Tony Z and so on. There were people my age. Frank Wilczek is my age. Nico Wolfenstein was younger, I realized, than I am today. You know, he looked old to me. And of course you'd say, well, obviously. And I find it very funny because I don't feel old, I'm sorry that I have to say that. And Nico Wolfenstein was a very wise man. He was an extraordinary physicist and very wise. And I in particular would work on this, understanding the origin of mass in the sense that you want me to reduce the number of parameters. Looking back, I'm surprised that I worried so much. Physics is about correlating physical phenomena, not so much about understanding your parameters. And I remember Lincoln was telling me, Goran, I think you're wasting your time. Think what happened to Kepler. Kepler wanted to compute the distances of planets from the sun. Spent all his life without a single, of course, logical thing. We know that was crazy. He says you're going to end up like that if you continue seriously, because first, the spectrum of these masses are very, very ugly. They're totally random, and the mixing angles, you must remember from Smirnov's codes, are very ugly. You're going to have a night theory that produces these ugly numbers? That's very unlikely. Non-symmetric theories predict non-symmetric. Good reason. Also, worrying about parameters should be the last thing you should do. In the 30s, Eddington was trying to compute alpha. He said, how can it be that it's 1 over 137? It should be order 1. He spent many years computing alpha. Didn't take him anywhere. I now feel the way Lincoln Wolfenstein used to feel. Okay, so I wake up with age. And maybe one of you guys disprove me. I actually feel that this is not the issue. I want you to appreciate the capacity of really, for you, making predictions on a different phenomena from the old one. This thing that Newton says, when he realized the same reason that the bloody stone falls down is the reason that Earth doesn't fall down on the sun. That's what physics should be about. So I would worry about the secondary. By the way, I would start worrying first after we test the theory of the origin of mass. To worry now, it's crazy because we may learn that the electron, I can now anticipate for you, we have just learned from the LHC, the WZ, top, bottom, and tau, third generation get a mass from the Higgs. That has been tested, not the first two generations. Imagine that's wrong. Now you have to start from scratch. Or better, go back to the 60s, before the Higgs mechanism. And you are very ambitious that you want to understand why electron is lighter than the muon. People wanted to do that. Now we know that was crazy. They could have done it because apparently bounces come from the Higgs mechanism. No matter how brilliant they were. You see the dangers of worrying about these issues, okay? So I'll put it and I'll try to emphasize it to you. Worrying about your parameters is the end of physics. That's when there is nothing else to do. So maybe 5 centuries from now or 25 centuries. I don't believe. I think we'll keep going on uncovering new phenomena. And look at this beautiful thing. So tell me, without doing a calculation, what will be the decay rate of this be? I'm asking the Higgs has a mass of 125 or 26 GeV, and let's take the fermion to be the electron. So whose mass is basically 0. I can ignore it, right? ME is MEV. MEV is 0 compared to 125 GeV. Think of it, really, it's 0, strictly speaking, because I'm doing it at the 3 level. If you want to be, fancy, then you should do the loop correction and so on, okay, which is there. So we can safely take that electron mass is 0. So what should be the decay rate without doing a calculation?
Then it's the mass of the Higgs.
Must be the mass of the Higgs, you've done it. And now you make the prediction because Yukawa is m electron square over v square times mh. But V is MW up to some G. This is beautiful for every mass in the world. So tomorrow we discover a new particle, you immediately write down the decay rate. Okay, this is the beauty of the Higgs mechanism. We'll have to come to that. So you understand how we are safe. Whether this particle is physical or not, I don't have to worry. It will not screw up gravity. It has a well-defined property. It's an interesting state to think about. The most important particle for me at this point is the scalar that provides the mass to, not to you and me. Proton doesn't get a mass from the Higgs. Okay, that Alexei probably told you. Quarks are very light. Proton is very funny. All the mass of the proton is because of this crazy motion of up and down quark and a little bit of this other quarks, right? And anti-quarks. In quantum physics, there is not just a particle, there is always a cloud. And of course, what else is in the proton? Is these gluons, right? They are messengers. So collectively, because of the strong interaction, you know, it's like you're running with a shopping bag, right? The shopping bag picks up the speed, so the energy of the shopping bag with you is large, even if it's very light. Okay, there is a huge kinetic energy. You know, proton is like a shopping bag, tightly bound. It seems it's not leaking. In modern language, we say that the quarks are confined. It seems. We have not been able to prove. Okay, so more or less, I think this would summarize the situation. We also went to the other gauge to understand what is going on. Or maybe I should say that once again to remind you. So I can also write this is a very interesting subject. By the way, I forgot to tell you, the reason that this becomes very interesting in cosmology, we cannot reach these temperatures in the laboratory and celestial objects. But we can imagine a universe. We can extend the temperature to the Big Bang, so we can have an interesting studies of cosmology. You know, this is this marriage between particle physics and astro and cosmology. Okay, so it becomes a question of the behavior of gauge theories in the early universe. Presumably, early universe was hot. Presumably, I say. You know what? Okay, as we go along, we'll be mentioning this. What is the temperature that we probed in the early universe? You have some idea?
10 to the 20.
No, that we probed.
Oh.
Not that we dream about. No, the only temperature is very interesting. It comes from nucleosynthesis. You're going to learn about that. So strictly speaking, universe, for all that we know, it surely was hot up to the temperatures of 10 MeV. Nucleosynthesis is around MeV. Proton-neutron mass difference and so on. You'll learn about that. Now, of course, we believe that there is no reason to imagine that there is some discontinuity. So we try to think of the field theory at high temperature. Fascinating subject, which I probably won't say anything until the end of the course. So we said a very useful gauge is what we call a gauge variable. I'm sorry, there's no gauge symmetry. It's phi unitary, which I can write as 1 over square root of 2, v plus h, e to the ig over v. And then I find out that g disappears. Well, it doesn't, it goes into the kinetic energy. It helps me see immediately that mg is 0, okay? So let's leave this. Well, I can't help anticipating, okay, at this point. Imagine that I now gauge the symmetry, which I will have to do that. What do you think? You see, this number Goldstone boson, when I gauge the symmetry. Imagine that I say that alpha is alpha of x. This is just to whet your imagination. Do you think this will remain a particle? You and I have learned that Nambu-Goldstone boson is a physical particle with well-defined couplings that can be produced in the laboratory and can mediate a long-range force. If I gauge the symmetry, what do you think?
By gauging you mean that make it local?
Yes. Alpha is alpha of x, I make. This is a side remark to that, a little digression. In this case, remember g of x transforms as g of x plus v. It will be alpha of x.
Yeah, I think the Gaussian bosonic gets eaten by boundary.
Precisely, that's a language that we use, but you can guess it here. If I can do this, I can choose alpha so that this disappears. It's very strange, right? But you can guess here. When I gauge it, it cannot be a physical particle. Simply cannot be, because I can find a gauge in which the guy doesn't exist at all. Okay, we'll have to worry about that. Now, so what we have to do. So I assume that you understood this U1 case. What we have to do is generalize it to non-abelian. So I will take this order. Well, I can erase it. We'll count. Oh. So now when we take the next step after U1 is SU2. I could take SO3, which are basically the same Lie algebras, they are different symmetries. SO3 means I have a vector representation, a triplet. But let's take a doublet. Let's take the what we call fundamental representation of SU2. Really, what is SU2? It's a two-dimensional field phi, which transforms into U phi, where U is e to the I Ta beta A. By the way, I can immediately generalize this to you SUN. You agree U is unitary, so I can write this e to the I Hermitian. So what I'm saying is that Ta is equal to Ta dagger because U is unitary. This is equivalent to UU dagger is 1. I'm taking SU2, determinant is 1, which implies that Ta are traces.
I don't know why I put it like this.
And then of course these are Pauli matrices, so without any further ado, Ta Tb will satisfy. Once I write like that and don't specify that they are Pauli matrices, I can then generalize it to a triplet or a quintet, whatever, right? As long as I satisfy commutation relations, I can do that. There is nothing wrong with that. So, and remember why I need a scalar field, because I don't want to break Lorentz symmetry. I got no option, so I took a doublet. I need to write a Lagrangian. How will it look like? It's embarrassingly trivial. I'm always writing one of the same Lagrangian. I feel like a dummy. Well, we keep uncovering things in spite of the simplicity. Okay, minus lambda. Now you can tell me. First I wrote phi squared, then I wrote phi star phi. So now I'll write phi dagger phi minus v squared over 2 squared. Basically the same Lagrange. Well, there is something hidden here a little bit. I'm assuming that this is the only invariant I can write. For example, I'm actually cheating you a little bit unless you're very good at group theory and you have a way of understanding why this is. How would you prove to me that this is the only way of writing the invariant? After all, I could write this also term. Look at this. Phi dagger Ta phi. Phi dagger TA phi. TA will be Pauli matrix, is okay. So I can as well say here TA is Pauli matrix. Properly normalized. Because this behaves as a vector, you can see that trivially. Or maybe you've never seen it, but I can guarantee you, you could go and check it. I don't write this. I'm supposed to write, by the way, if I want to have a normalizable theory, what that Hoff taught us, it's okay, write this dimension 4 Lagrangian, but write all the invariant terms. Because if you don't, you'll regret it, they will reappear. And they may appear as infinity, there is something called a normalization and so on. So the rule of the thumb is, write all the terms, but I don't write this term. I could even write term like this. I could write, in principle, phi transpose I sigma 2 phi. Do you know that this is an invariant? Everybody knows that this is invariant. If you don't know, let me know, please. Tell me, raise your hand if you don't know that this is an invariant. How do you know this is an invariant without even doing a calculation? Well, it's easy to do a calculation. This is, if I write phi, I have many ways of writing. I can write phi up, phi down, or I could write also like this. So what I'm doing here, I'm anti-symmetrizing, right? This is really, this is how you wrote the spin zero state in quantum mechanics. You have anti-symmetrized. You took a spin half and you anti-symmetrized it. You actually wrote it like this, but you never used this notation maybe up to now. Hopefully you did. It's very easy to see this is an invariant, but I don't write it. Why? I don't know, let me think. This could be a homework to let you think. The answer is, of course, that they somehow have to reduce to this, right? Because what I'm saying here is correct. Okay, so what will be my vacuum manifold? I'm not going to try to draw the picture now. This is a bloody higher dimensional. Can you guess? It's the set of fields phi 0 dagger constant phi 0, which is v squared over 2. I wonder whether you can see it immediately. It's not trivial, but maybe it takes a little thought.
Like a forest view. Like a forest view.
Not 4. Almost. Sergei almost got it right. Why? So I could write phi. Remember, I'm going to put this 1 over square root of 2. So I could write like this, phi 1 plus I phi 2. These are complex field. Phi 3 plus I phi 4. So phi dagger phi is 1/2 sigma phi I squared 1 to 4. So this condition really translates into sum over phi I 0 squared I 1 to 4 is v squared. That is, we had S4 and S2. Like usually in life, the truth lies in between. You know, when you have opposed views, right? If you start discussing politics or religion, most of the time the truth is it's S3. I have 4 coordinates that live. When I have 2 coordinates that live on a fixed radius, that's called S1. When I have 3, that's called S2, so this is S3. Okay. So this is S3. So, what I can do, let me erase this. I will maybe leave it for the, let me not answer the question I asked. So how can I write my phi? I can do this phi renormalizable and write it as 1 over square root of 2. I can write like this, v plus H plus I G3, G1 plus I G2. Just a notation, the same as before. I fixed my vacuum. It's with the vacuum theorem. I took it with a phase 0. You take it e to the I pi over 2 if you like, and so on. We will see that physics does not depend on that. I will do it in the gauge case. I will show you explicitly. But by now you believe me, because obviously the symmetry tells you at any point, like in the two-dimensional case, it doesn't matter whether you choose plus v or minus v. It's like saying what I call left. It's just a definition. I can call left, right, and so on. The reality cannot depend on my convention. So can you guess what the mass of H will be? Well, notice when I substitute that, I will get the potential will become, so this is my V, will be lambda over 4, and then it's going to be V plus H squared plus sum 1 to 3 GI squared, obviously, I'm taking phi dagger phi, G1 squared plus G2 squared, okay? Minus V squared, everything squared. This is lambda over 4, 2VH plus H squared plus sum over G squared, GI squared. Notice, always one and the same thing. Regarding H, I'll get the same mass as I got in the real case. If you forget about the G, this is the potential I wrote in the discrete case. If you forget that there are 3 of them, it's the same thing that we got in the U1 case. What will be the mass of G? You can see immediately. It's 0. There is no mass term for G. MGI is 0. I have 3 massless particles. These are my 3 Nambu-Goldstone bosons. And I'll convince you now that they're really what we call Nambu-Goldstone bosons. The stuff that I was today talking about fermions, Higgs, and so on decay, this was just to prepare the set. Don't worry, we'll do this at the depths, in depths, and probably we'll bore you with that. You were not supposed to learn it really today. If you did, so much the better. Now why? Remember how I said I will have spontaneous symmetry breaking every time when a generator does not annihilate the vacuum. Why? Because this will be equivalent with the U that accompanies this generator acting on phi 0, not giving me back phi 0. Vacuum is going to be non-trivial, it's going to carry charge, symmetry will be broken, okay, in that particular direction. But my generators are Pauli matrices. You see what I've done? I've taken phi 0 in this case. I didn't specify it, but now you see, I took it like this. Right? Phi 0 is constant value of the fields when I don't include the field. Now TA are sigma A over 2. And obviously Pauli matrices, when it acts on phi 0, will not give you 0. But you know your Pauli matrices, there is nothing I have to do. You have 3 broken generators. And according to Goldstone, every time you break a generator, we are proving the theorem, by the way. I got 3 broken generators, I got 3 massless guys. I could have seen that maybe in a slightly different manner. But I don't know if I wrote this intelligently. I'm not sure. I think I should have wrote this. Okay, forgive me. Suppose I write I G1 and minus G2. That's the same, right? That's just the and I write minus IG3, my privilege. Just write on the side if you're writing. I could have done like this, you agree? Why? Because I can go now in what we call the unitary variable. I could have written this like this. E to the I, GI, TI, maybe my normalization is not, I can also write like this. Complex field I can write, remember, as a true real or absolute value in the phase, but so I can write a doublet. Why? If I expand this, I don't know if I want this 1 over square root of, I don't know what I want here. I'm sorry. I can't decide. I need your help. If I act with this on this, what am I going to get? The leading term, right? So I expand this. So this is simply 1 plus I, GI, sigma I over 2. What will I get? I will get V plus H, you agree? Now sigma 3 will act as sigma 3. G3 will appear where? It will appear here. So I'll get some kind of half, okay? Notice I will get minus I sigma 3 over 2. Normalization would be a little different. So I should, let's think how to normalize it, okay? It doesn't matter, I don't have to agree with myself. This is just giving names to the fields. And here, what would I get here? Sigma 1, right? You see? I will have I over 2 G1 because there is a Y and sigma 1 is real. And sigma 2 has a minus I times I, or will be plus G2. I think 1 over half plus G2. But I goofed, there is some square root of 2. Forget it, doesn't matter. All I'm showing you that I can always write like this, you agree? I don't know why I try to be agreeing with myself. Don't worry about that. It's irrelevant. I'm choosing variables. They don't have to have the same name. Okay, as I've chosen. But you can see, just by properly normalizing, I get it okay. Why this is very useful? This particular way of writing it because phi, so-called unitary dagger phi, doesn't have these guys anymore. They disappear. This is 0 V plus H. Sorry, it's just V plus H squared. These guys are obviously massless. Where did they go? They went into the kinetic term. Right? That's what we found in there. I'm just sort of trivializing, generalizing in a trivial manner the U1 case. Notice you'll be able to do it for, if I do SU3, right, you will have Gell-Mann generated, so on. You can always repeat this trick. Okay. We'll do a few examples so that you familiar yourself with it, so that you sort of start feeling at home, that it gets into your fingers. And it's not something formal. And this is how the Goldstone theorem works. You see, there is always a field associated with the generator which is broken. We say that the generator is broken. It doesn't, no, it's different from zero, not from 5, 0. Why did I say? I was clear there. All I need is a carry charge. Sigmas are charges, right? We often use this language. Not a good language, okay? There is just one charge. Charge normally is a diagonal operator. When we are very careful, then we should always remember that charge is that particular, it has to do with the rank of the group, right? It has to do with the Casimir. It has to do with the number of the generators that you can diagonalize simultaneously. In SU2 is just one. In SU3,
2.
It's 2. In SU4, 3, and so on. The rank of SUN is n minus 1. So in SU3, there are 2 members of Cartan subalgebra. And you typically get 2 invariants. You can sort of start guessing why I can get only 1 invariant here. Rank is 1. Okay, there is a group theory argument. So this way of seeing is very useful because every time the generator is broken, if generator is not broken, this would vanish. There would not be a Goldstone boson, you see that? If sigma annihilates the vacuum, then this guy will not appear there, okay? As if I didn't put it, so. You see, this is like the vacuum. H just accompanies the vacuum, okay? It has the same structure. Whether I put H or not, it has the same structure. Higgs field maintains the structure of the vacuum. It's just a little sort of, you know, excitation about the vacuum. That's what the Higgs field does. It lives there. You and I are happy with this. There is no tunneling, right? We've learned that if you're in the discrete theory case. We can live around that ground state safely. So we have generalized the theorem. We do a few more examples. For example, let me ask you, you make a guess. If I take SO3, which is equivalent to SU2 with a triplet. So imagine that I have a triplet of scalars. I take something like this. Phi 1, phi 2, phi 3. A vector. So we say here, I forgot to say, SU2 is broken down to nothing. There is identity. Why? Because all the generators are broken. TA acting on phi 0 is not 0 for all 3 of them. All of SU2 is broken. If I have a vector, what do you think will happen? Same thing? I have to think that I want to do it or give you as a homework. I have to think about that. Maybe it's more fun if you do it as a homework because when you are taught, you don't learn the same way as when you do it yourself. But you could guess. You see what I've done here? I said I can always choose the vacuum like this. But if you don't believe me, by the way, you show that you can do that. You can do it by rotation. I can say, you know, this will be 5 Goran. But you know, I don't know. Sergio says, no, I don't like your vacuum. For example, mine is like this. Well, you can do that. But then comes Nora and she says, no, I want this kind of vacuum. And maybe put phases even. Well, you can prove, you can always go by unitary transformation from one to the other. It's obvious. The same way that you can orient a vector in one direction. Whatever vector you give me, I can take it along the z-axis. So here, in other words, phi 0, I can choose in one direction. I'm not teaching this, I'm just giving you a flavor, okay? This is another way. You know, I want you sometimes to try to get a flavor. Will all of the symmetry be broken? If I take my vector along the z-axis, is all rotational symmetry broken? No, there is still U1, what we call SO2. I can still rotate in the plane of x and y. For example, in this case, how many generators will be broken? 2, not 3. Because the guy around the z-axis. So for example, I would expect how many number of Goldstone bosons? 2, if the theorem works. Okay, it's nicer. There is something for a physicist, of course. If you're mathematically oriented, you don't care about examples. You want to have a proof. But I sort of, if I had been good at mathematics in high school, I don't know whether it happened to you. You know, it's math that took me, even in the elementary school, into physics. But I was just better at doing physics, and I could see that whenever I tried to. Actually, there was a period in the 80s. You know, if strings are correct, then you and I live in 10 dimensions. And we have to compactify the other 6 dimensions. And they should be some funny topological objects. Oh, maybe not. They were imagined. So I actually spent some time working on this. They were called Calabi-Yau manifolds. And I could see that it was better that I decided to be a physicist. It was a very mathematical subject. I had to learn differential geometry and so on. So I like to do the theorems but through examples, okay? Let me think whether I'll prove it or not. Also because I'm worried, because sometimes you learn the formal thing, but you don't get a feel for it, okay? Okay, I think I can stop here. Either we'll do it in the homework or we'll do it this very carefully. You have to be sure, we'll do a number of such examples. We have to have a, very, very clear picture of what is going on. Symmetry breaking is the essence. Spontaneous symmetry breaking of modern particle physics. That's somehow, if you had a field theory course, of course, I wouldn't have to teach it here. But I have to make sure that you really grasp it. Anyway, you may have questions. What I wanted to tell you, we canceled this thing today because Vicharit wanted to come for this. I'm going to give this talk regarding this. I just wanted to tell you the talk, any talk you go to should be over your head anyway. But this will be basically on the standard model. It will be very thing having to do with the Higgs mass. And maybe a little early for you guys because you don't really know the Higgs. But already today you got a feel of what this Higgs field will be. Okay, just to tell you, and I think you asked me, Hassan, I've learned it's going to be in the sort of old CISA, in this new institute, at 4 o'clock, if anyone.
We have the tutorial at the time.
No, it was cancelled.
No, but it's the one of GR, no, standard model, GR.
Oh, he put the tutorial.
Which is the...
And there was a tutorial.
But why didn't you tell him not to do that? I don't understand. We asked just to give you the freedom, the important thing is, you see, I've been, this I find, so he didn't know. But I thought Paolo, maybe he said it without Paolo. You see, the idea here is actually, I'm told that you guys are obliged to go to colloquia. I don't like that. I'm now debating with my colleagues here. And it seems, okay, we're talking a lot with Paolo. I think I convinced Paolo. I'm not sure. We'll see. I don't like the idea that you're obliged to go there. I think it's good, however, that you have the freedom and the possibility to go for the talk that may be of interest. So it's good to make sure that the talks which are of general interest are not clashing with your classes that we try to do. Anyway, any questions?
What did you mention for the homework is about proving the Goldbach theorem?
Well, I'm not sure. I'm not sure. I'm not sure whether I'll do it or ask you in the homework. Well, the proof of I'm not sure I should ask you in the homework because you're going to look in the books. That it's very unlikely that you prove on your own without looking in the books. When I give you the homeworks which are in the books, I hope you don't look in the books because you learn nothing by looking in the books. But that's up to you. The possibilities, the homeworks, I'll give you some homework that you have to think that you won't find in the books. I want to make sure. There will be some homework that hopefully all of you can sort of grasp what is done. We need some homework that hopefully maybe none of you do, right? We have to know. We have to you have to know also what is hard, what is not hard. Right? So don't get discouraged if the homework looks very hard. You don't know how to solve it. It's okay.
There was a viral picture on the internet where a professor gave as a homework assignment that please reconcile general algebra in quantum mechanics. This was a homework assignment.
Rare.
Obviously it was a joke.
Sorry?
Obviously it was a joke. Oh.
But where did you see it? No, I know.
It was probably the undergraduate homework assignment. Yeah, okay.
Somewhere. No, I'm just curious who had this.
It's in US.
All right. Well, there is a beautiful book, if you like, this kind of thing. It's called Uncle Petrus and Goldbach's Conjecture. Any of you heard of it? It's a wonderful book. By the way, mathematicians don't like to talk about it because this is the hardest problem. You can imagine, the easier is to phrase the problem. It's more or less like the physics you're working on. I tell you, you will know that you work on something fundamental if you can go to the bar and tell Aga about it. Then you are working on something fundamental. If you go through not by you claiming that. In mass, of course, the simpler the problem, the harder. So Goldbach conjecture the following. Who knows Goldbach conjecture? So what he conjectured is that?
Even numbers greater than 2 terahertz is written as 2 prime numbers.
Right, like 87 plus 1 or 5 plus, it may be more than one combination. It has not been proven yet.
Yeah, it has been proven that it can be written as 3 prime numbers, but not 2.
And you can see it's surely a bloody hard. People don't know even how to start. So the book is beautiful because Uncle Petrus gives his nephew this as a summer assignment. You should read this book, okay? I'll send you the information if you can get hold of it, okay? It's a wonderful book. Any question, just in case, because we are turning off the... any question that would be a public interest? We turn this off, machine. It's enough for today.